Off you go.
Okay, yeah, thank you. See, I wanted to talk about a little bit about how one actually goes about proving this. So I guess where we got to last time is it's enough to classify maps not into B, but into an ultra power of B. So you're classifying the approximate morphisms instead of actual ones. I should point out too, as I said last time, the domains here can be fairly general, and don't worry too much about what the exact hypotheses are, but just think of things like C of X, a group algebra for G amenable, or a cross product, or the things that are typically very far from simple, or for instance, I guess for this one, to have a faithful trace, you need to know X has a G invariant measure, but nothing anywhere close to minimality or freeness that you would need to get simplicity. The hypotheses on B are actually rather restrictive, but you can think about just the UHF algebra if you like, or some other really nice AF algebra. This later work with Carrión, Gabe, Tikuisis, and White does relax the conditions on B a little bit to the case B is Z stable with possibly several traces at the expense of slightly more complicated K theory. But yeah, I'll stick with this case. It simplifies things quite a bit. Okay, but well, as I did last time, I'll take M to be the von Neumann algebra generated by B in the GNS representation of its trace. And kind of the overarching goal here is to study B by studying this von Neumann algebra. You somehow want to take properties of the von Neumann algebra completion and its natural von Neumann algebra topology, say the 2 norm or unbounded sets, that's the same as the Straun operator topology, and turn it into properties of B with the operator norm. There's of course law in history by studying C-star algebras, by studying how they embed into von Neumann algebras. One of the most famous ones is the C-star algebra is nuclear if and only if its bidual is injective or semi-discrete, hyperfinite, any of these. There's also been a handful of results going the other direction, like actually what Jesse talked about. You can use properties of exact C-star algebras to show certain 2-1 factors are solid. I think it's Suzuto Ozawa. But this idea of transferring back between C-star algebras and von Neumann algebras can give you a lot of leverage. So the way it's done in this setting is going to be by looking at these ultra powers. So you have the C-star algebra ultra power, bounded sequences in B, modulo the operator norm null sequences. And this von Neumann algebra ultra power of M, the bounded sequences in M, operator norm bounded sequences, modulo the 2 norm null sequences. And I think where I ended with was you have this natural surjection of the C-star ultra power onto the von Neumann ultra power. And this has some natural, well, J is by definition the kernel of that. So this is the usually known as the trace kernel extension. Probably really started being studied systematically with Matui and Sato about 10 years ago. And actually, a lot of the progress in regularity theory over the last 10 years has come from, a very delicate analysis of this extension, in particular ideal. Under various conditions, Matui and Sato managed to take McDuff's property, so it's R stability for the von Neumann algebra, and somehow pull it back to Z stability of the algebra. with somehow the idea being both properties have characterization in terms of central sequences, either in the 2 norm in the operator algebra side, the operator norm in the von Neumann algebra side. So somehow it's the same property, Z stability and R stability, just with different metrics. And so here, so it's JB is by definition the kernel of this quotient map, or by whatever first isomorphism theorem, I guess you can give an explicit description as the 2 norm null sequences modulo operator norm null sequences, or I'll write it this way. It's the sequences going to 0 strongly in the GNS space modulo the sequences going to 0 uniformly. So it's somehow encoding exactly the difference between the von Neumann algebra world and the C-star algebra world. And C-star algebra is willing to give up epsilons and operator norm, and von Neumann algebra is you can do it in strong operator topology. Okay. So the goal of the classification theorem here is essentially to follow that strategy, but take the Kahn's theorem on the uniqueness of the amenable 2-1 factor and somehow lift that back to some kind of uniqueness of the, I don't know, whatever, classifiable Q-stable unique trace algebra. And with the K-theory, it's going to show up, and the K-theoretic obstructions are going to appear somehow with this ideal J. Okay. So try to make that a bit, spell that out a bit more here. So first step is the von Neumann algebra side that you have. So under A and B is in the theorem, there's a trace preserving map, let's call it theta, into this von Neumann algebra quotient, which is unique up to unitary equivalence. I mean, yeah, or sorry, I keep switching back and forth. Yeah, it's on the, well, if it goes to 0 strongly, it's sequence going to 0 strongly has to be bounded. So it's happening in the unit ball, and then the 2 norm and strong operator topology agree there. Yeah. But yeah, 2 norm or operator norm, same algebra. Yeah. So what happens is you get this existence of a map into this von Neumann algebra ultra power, so it's quotient to be omega up to unitary equivalence. Or I guess what you prove is up to 2 norm approximate unitary equivalence, but then you can vary the approximations in the ultra power and get actual unitary equivalence. So this, you can find several variations of this in the literature over the years. All of them go back to Kahn's theorem. I won't say really exactly how to do this, but the point is, if you're mapping A into a von Neumann algebra, you're free to replace A with its von Neumann algebra completion. Any map here will necessarily factor through the von Neumann algebra completion of A. And if I had a map from the von Neumann algebra completion, I could just restrict it back to A. So it's really a statement about maps between von Neumann algebras. If A is nuclear, this is hyperfinite. So you're really asking for maps from hyperfinite von Neumann algebras into 2-1 factors. Classify these by their trace. And that goes back to actually Murray and von Neumann even. You reduce from the hyperfinite case to the finite dimensional case, and then the structure of finite dimensional algebras eventually reduces to the classification of projections. And projections in 2-1 factors are determined by their trace. Okay. So when I said on Tuesday, I talked about this, the classical approach in terms of these tracial approximations, where you get this tracially large approximate corner of B with nice approximation properties. This trace kernel extension is somehow playing the role of your this tracial decomposition of B. You have this tracially large part, M omega, and this tracially small part, J, which you have to show doesn't get in the way too much. The key payoff is that tracially large part is now actually a von Neumann algebra. So you get these finite dimensional approximations at the von Neumann algebra level straight from Kahn's theorem, which allows you to bypass a lot of the machinery to build this tracial AF structure. And also, it doesn't need projections at all. It's because just nuclearity alone gives you this hyperfiniteness of the von Neumann algebra. Okay. Once you get the von Neumann algebra result, then you somehow need to lift along the extension. It's actually done in 2 steps. So you have this map theta, which we fixed from A into M omega, that realizes a trace. I want to know I can lift that to a homomorphism from A to B omega. So you have this map lifting problem. Can you lift a map from a quotient back to the extension? Well, in full generality, that you can't. Of course, the first obstruction you're going to run into is if A had a projection of trace a half and B omega doesn't, there's not going to be a lift, because the lift will necessarily be trace preserving, because it was down here. But so there's K0 obstructions to start with. And under the UCT, it turns out those K0 obstructions vanishing is enough. In our case, they'll vanish from the Q stability. But sorry. In general, there's an obstruction to lifting. And it comes in this extension group, X, A, JB. There's some separability issues, but I'm going to ignore those, which can be realized actually as a KK group, like this. KK maps from A to the suspension of J. So I'll just call that angle bracket theta, the obstruction to this lifting problem. So it turns out theta, you don't actually need this, but it's, this obstruction is actually a well-defined thing. It doesn't matter how you realized the map into the von Neumann algebra to start with. You actually get a well-defined invariant here. That's not a general fact. There's something really special about the von Neumann algebra quotient that's making that work. And also the more important one, this obstruction vanishes if and only if theta lifts to a star homomorphism. So you end up with this computational problem of, this is actually where most of the work is in this step. But you end up with this computational problem. Once you know this, you just have to compute some KK element, and the UCT gives you a lot of tools to do that. And without the UCT, computing these things is nearly impossible. But under this UCT assumption, which we have, that obstruction will actually vanish automatically in this Q stable setting. Okay. Third part, once you have at least one lift, you want to know, existence and uniqueness theorems for lift. The lift you choose is not going to be in any way unique in general without really strong conditions on what A and B look like. There's several non-canonical choices made in the construction. There's So what you need is actually existence of uniqueness results for a lift of this given map. Now let's write down what it comes out to being. Given at least one lift psi to start with, lift of this given map theta, the set of all lifts up to unitary equivalence actually form a group. They're parameterized by, the group structure depends on the choice of psi. Psi will play the role of the zero element, the one thing you chose. But this turns out to be in natural bijection with, well, natural modulo choosing psi to start with. This KK group, KKA, JB, sending phi to, well, the notation I used, last week, it's this formal difference of phi and psi. So it was this generalized morphism from A to J. Which you think of as representing phi minus psi. So this is where the K-theoretic obstructions are coming in. This KK obstruction to lifting, and then once there is a lift, this other KK obstruction to, classify the lifts. In the final step, you use the universal coefficient theorem to actually compute what these KK obstructions are. Actually, 2 and 3 and 1 don't depend on UCT. It only comes in at this stage. But what you want to do is somehow relate these KK theory of J back to something involving B, or B omega at least. So ideally, KK of B omega would be good enough if you could manage to do that. But under UCT, you'll be able to relate it back to the K theory of B omega. Okay, but I won't go through this computation, but so what the UCT will give you is you can compute, say, this group in terms of the K theory of A and the K theory of J. The K theory of J, by the chasing around the 6-term exact sequence, can be computed in terms of the K theory of B omega and the K theory of the quotient M omega. K theory of von Neumann algebras is actually very well understood. The K0 group of 2-1 factor is R, because the projections are classified by their trace. And the K1 group is 0 because of Borel functional calculus, all unitaries have logarithms. So the unitary group is path connected. And if you now apply the UCT and chase around the 6-term exact sequence, what you get is the K0 of B omega, or the K0 of J, is exactly the trace 0 elements and K0 of B omega. And the K1 of J turns out to be K1 of B omega. Okay. Then as you put it together, what you end up with is, once you know there's at least one lift, the maps from A to B omega are in bijection with maps on K theory vanishing on the trace. But then by translating that, that's also equivalent to maps on K theory preserving the trace. And you get back to the classification from maps from A to B omega. And then the final step, I guess, is intertwine to remove the omega and get back to classification of maps from A to B. Okay, so that's just sort of the broad strategy behind this. I think what I'll actually go through is what step 2 looks like. There's a lot of the same machinery in step 2 and step 3, but it's somehow easier to see in the case of just proving one lift exists. Is that low enough still, or does it go? Okay. All right. Sure. Yes. Right. Yeah, so I'll talk about the second part, the proving the existence of a lift. I should mention, I suppose, this K-theoretic computation here is where a lot of the hypotheses do come in. As you start replacing Q stable, if you replace Q stable as Z stable, there's extra K-theoretic information that falls out of this computation. I guess also if you replace unique trace with possibly several traces, step 1 becomes a lot harder as well. But yeah, it's part of it why we do want to stick to this case to not deal with those issues. Yeah, so this statement is true without UCT, that the KK element vanishing is equivalent to having a lift. But yeah, UCT comes in to compute this element. What ends up happening, well, even under more general assumptions in here, under UCT, this vanishing will be equivalent to the existence of a K0 lift, K0 map, making that triangle commute. So in the general case, you're trying to prove an existence of a map from A to B. You assumed already you had the K0 map from A to B, and that's what will force it to vanish. In this Q stable setting, somehow the B is big enough that the existence of some K0 map will come for free. But yeah, UCT is definitely used to compute that X obstruction. So I mentioned Tuesday I mentioned your starting point to get a map from A to B omega comes from the quasidiagonality theorem. What I'm going to talk about too is essentially, what I'm going to talk about here is essentially a proof of the quasidiagonality theorem. Somehow it's one of these things that quasidiagonality was always one of the main ingredients in classification because it somehow gave you something to start with in an existence result. And then at the end of the day, once we really understood where quasidiagonality is coming from, it turned out you somehow didn't need it. You could just prove the existence results directly. But yeah, this is really coming from quasidiagonality in one way or another. Okay. I'm going to restate this once more. Instead of asking for a lift, there's a natural pullback extension here, which you can consider instead. Where, if that extension is called EB, that one's theta star EB, say. And in this case, where theta is injective, E can be written explicitly as just the preimage of A under this quotient map. So it's Q inverse of theta of A as a subalgebra B omega. That map there is just the restriction of Q. This is the inclusion. Okay. Right. So I'm going to essentially cut out the lower extension here. A map from a lift of theta well, and the quotient takes values in the range of theta, so any lift of theta necessarily takes values in E. So and it turns out, so if having a lift here is equivalent to having a splitting for this top row. So theta lifts to some psi if and only if this pullback extension splits. Meaning there's a, let's call it psi naught from A to E, which lifts the identity on A. So it's actually the splitting of this extension that we're going to state things in terms of. And I'll actually do this in a more general setting of just abstract extensions of C-star algebras. So here, we'll take, well, A and I will be separable, I stable. The A I apply all this to is going to be the A from the theorem. The I is going to be, I guess, some large separable subalgebra of J. And I'll assume A is nuclear for convenience. It doesn't have to be to make the theory work, but it'll simplify a couple steps later. Okay. Consider extensions of the same form of A by I. So we'll fix the I and the A and look at all possible ways of, setting I as an ideal of something where the corresponding quotient is A. All right. So I'm going to look at extension. I'm going to turn this set of extensions into an abelian group is the goal of this. Like you do for extensions of modules or abelian groups or things like that in algebra. So first, the equivalence relation. Two extensions are isomorphic if, so I have an extension I to E1 to A, and an extension I to 2 to A. So the first thing you want is the algebras themselves should be isomorphic, or the extensions themselves. But you want somehow that isomorphism to be compatible with how it was built out of I and A. If we're dealing with modules, the way the usual notion of isomorphism is induces the identity on both the ideal and the quotient. That's a bit too strong in this non-commutative setting. Ask that it restricts the identity on A, and instead of being completely trivial on I, it'll be inner. So it's given by conjugation by some unitary. So this is for some unitary in the multiplier algebra of I. Okay. And also you have a notion of have a natural addition given by direct sum. So So I'm not going to write down the addition, but it comes down to a 2x2 matrix direct sum where you use that the compacts is isomorphic to 2x2 matrices over the compacts. Since all automorphisms of the compacts are inner, it doesn't matter in the end which isomorphism you choose. Okay. If you know extension theory for, say, modules, the direct sum is very equivalent to like the bare sum that you do in that setting. I think it's called the bare sum. I've got the words mixed up, but the usual direct sum operation and extension theory. Okay. The problem with this is the equivalence relation isomorphism is entirely uncomputable. There's basically because of lack of cancellation that you want something slightly, or if you like, I mean, if you just took extensions up to isomorphism, it'll form a semi-group. It won't have identity. It won't have inverses, and you could take the group completion of that. What will come out is this weaker equivalence relation. E1 is equivalent to E2 if there's a split extension, E, so that E1 direct sum E is isomorphic to E2 direct sum E. Now, of course, if you really do have a group structure, this would imply E1 equals E2. But you don't have cancel. This does not imply E1 is isomorphic to E2 in the sense of isomorphism. That this building in this cancellation is needed to get any kind of nice algebraic structure on this. Okay. This extension group then is all extensions up to equivalence. So this is a abelian group. Here's why I want nuclearity. It's if you don't have any nuclearity, it's an abelian monoid. Inverses won't exist in general. There's a theorem of Arvidsson that the invertible elements of this monoid are exactly the extensions which have a completely positive splitting. And then the invertible elements, of course, do form an abelian group. When A is nuclear, you get a completely positive splitting automatically by the Troy-Afros lifting theorem. That's the only reason for nuclearity here. It'll show up elsewhere, but. Yes. Yes. So this split is, via star homomorphism. So having an inverse will be equivalent to just having a completely positive splitting, but the elements we're quotienting by are the ones with the star homomorphism splitting. Yeah, because the star homomorphism splitting is what you want to get the eventual embedding back in, because you want to, star homomorphism A to be omega. Yeah. The inverses eventually come down to Stein-Spreen's theorem. You take your complete positive splitting, dilate it to a homomorphism into something, and play around with it a bit. And basically, that completely positive splitting is 1,1 corner of a homomorphism. The 2,2 corner is used to define the inverse extension. So I'll call some notes here. So if E is some split extension, the class of E in this X group is 0. You sort of designed that to be true. You force the split extensions to be the 0 element. However, the converse fails quite badly. Then there exists a split extension so that E direct sum this other extension splits. But the second term splitting and the direct sum splitting does not actually imply the first term does. It's annoying, but it's the way it is. Which is what makes this problem hard, even if you magically can compute this X group, which was done largely by Kasparov, well, homotopy invariance and half exactness and all these kind of properties, and then Rosenberg and Choquette packaging in terms of the UCT. But even if you can compute that element and show it vanishes, it doesn't tell you that theta has a lift. It tells you theta direct sum some complicated thing has a lift into some complicated algebra, which has nothing to do with the codomain we want. That getting rid of that second summand is what the proof comes down to. Maybe before I think I have time for this. I want to give a kind of a concrete example where there's a very concrete example where this does fail when I is the compacts even. So A is going to be the continuous functions on a closed disk, and I is the compact operators on, let's name the Hilbert space for once. What are all 2? Let S be the unilateral shift. Then, so I'm going to build the extension by well, it's the C-star algebra generated by no, it's we consider what's called roll from continuous functions on the disk into the Culkin algebra by functional calculus. Well, maybe S bar for S in the quotient. So the spectrum of S bar, I mean, in the quotient S is a unitary, so the spectrum's on the circle. It's normal and the spectrum's on the circle. In particular, its spectrum is contained in the disk, so you can define that map. So the extension is going to be coming from lifting this. So consider, so I have the compacts inside B of H, inside the mapping to the Culkin algebra. I have this map from C of the disk given by functional calculus on the shift, and this pullback extension here. So similar to what we had before. And call that E. Right. Then so there's a deep theorem that X is a homotopy invariant. So since the disk is contractible, C of the disk is homotopic to the complex numbers, and this becomes 0 because of the statement that basically because projections in the Culkin algebra lift the projections of B of H. And so in particular, E is 0. But I claim it can't actually split. So think about what a splitting would give you. I mean, that's generated by a normal contraction. So if you have so you really only care what happens to the generator. If you had a splitting, your generator would go to the generator would go back to E, then down here, you'd have a normal contraction, which is a compact perturbation of the unilateral shift. So if E splits, there exists a normal T in B of L2 with S minus T compact. But normal, so S and T are both Fredholm now. Index of S has to be index of T by the index is invariant in a compact perturbation. If S is the shift has index -1, since T is normal, it has index 0. No splitting exists despite this X obstruction. Right. But somehow it stably does have a splitting because it vanishes in X. What you actually do end up with is, if you look at MZ and bounded operators on L2 of the closed disk, say with a Meg measure. So that's multiplication by Z. It's the operator. Then, well, there is a normal operator T. Maybe I shouldn't use T again. Let's call it R, acting on L2 direct sum, big L2, with the shift plus the multiplication by Z being a compact perturbation of R. So the shift direct sum and normal operator actually can be written as normal plus compact, which is really strange. Somehow that extra normal summand is absorbing all the index information from the shift. There's actually some history behind this example. It's the first, I think the proof of this really came out of originally Brown-Douglas-Fillmore theory. It's because it's essentially, direct sum is essentially normal operator and the spectrum is connected or simply connected, that it has to be normal plus compact. There was a direct proof of this. I think it was due to Donovan not long after, an operator theoretic proof making heavy use of quasidiagonality of the shift. And somehow that proof actually led to things like, it was sort of the first grain of things like homotopy invariance of quasidiagonality and the modern proof of homotopy invariance of X. This turns out to be a rather subtle example, even. It's even Donovan's proof where he does it just by operator theoretic methods is incredibly difficult. It's you somehow can't just write down the operator very easily. Okay. But what I've been hinting at through all this is some notion of absorption that is what you need. So an extension E is absorbing if for all split extensions E prime, E absorbs E prime. Once you have absorption, it is true that the vanishing of NX implies existence of a split. E absorbing and vanishing in X implies E splits. All right? Because vanishing on X means E direct sum split extension splits, but E direct sum that split extension is just E. So there's a nice, most famous example here. If you have an extension by the compact operators, this is absorbing if and only if it's essential. Essential is every ideal of E intersects the compacts, or equivalently, the induced map from A to the Culkin algebra is injective. And that's exactly what failed here. This map is not injective. If you viewed it as functional calculus on the circle, which is what you normally do, you'd end up with X of CFT compacts. That's actually the integers, basically by the index map. So if you're allowed to enlarge your space too much, you can lose all the index information. When you have essential extensions, you can't. Okay. I'm basically out of time, I think, that I'll just get to the punchline here. There's a result of Elliott and Kusarovsky. Well, there's been several generalizations of White-Kolesky's theorems over the years. There's one in particular of Elliott and Kusarovsky, which under very general, gives you very general methods for checking if an extension is absorbing under some nuclearity hypotheses. I'm not going to state their actual theorem, but I'll say how it applies. Well, this extension we're interested in, that too, I call it E to A. I think it's still on the board. Yeah. Okay, maybe it's not. But the pullback you got, you took the map from A into M omega, took the pullback of that extension. This will be absorbing. Modulo separability. What you actually show is every separable subextension of this is contained in a larger separable subextension, which is absorbing. But yeah, the separability works out in the end. Right. So because once you get absorption, and this is somehow where most of the proof is happening in the end. This is a difficult analytic result. Most of it's due to Elliott and Kusarovsky. And which is actually goes back farther. It's sort of large parts of it are based on Kirchberg's work on the purely infinite classification to get the absorption theorem. But once you get that, this pullback extension vanishing in X does give you a splitting, which gives you an embedding A into B omega. And probably out of time. Yeah, so I'm specializing to the case. B is a UHF algebra Q is what recovers this Tikuisis White-Vinter quasidiagonality theorem that separable nuclear UCT algebras with a faithful trace are quasidiagonal. Okay, that's a good place to stop, I guess. So thank you.
And thank you, Chris.